Welcome back. In this section of the lecture, I will describe another effect that limits the dynamic range of receivers, which is intermodulation distortion. Intermodulation distortion can be measured when we fit our device with two tones of equal amplitude, different frequencies but equal amplitude. And in this case, we will focus on these terms highlighted here. Now, these terms, which I have rewritten in this slide, are terms which depend on A1 squared A2 or A1 A2 squared. So if we make A1 equal A2, meaning that we are feeding our system with two tones of equal power, it turns out that the dependence is cubic for both these terms and as I say, these two terms are called the intermodulation products or third-order products. Now, if we look at the output spectrum of the device, we'll find that this spectrum looks like this. We will have a strong line at frequency omega 1, another strong line of equal power at frequency omega 2, and the two intermodulation products will fall at the sides of these two spectral lines. It turns out that the frequency spacing between all these four lines is homogeneous, right? It's always omega 2 minus omega 1. And here we will define P out as the power of the desired signals at omega 1 and omega 2, and PIMD as the power of the intermodulation signals at 2 omega 1 minus omega 2 or 2 omega 2 minus omega 1. And R is the ratio between those two powers, or if you want, is the difference in dB. And this is called the IMD suppression. The intermodulation products, if we analyze the equations that we have derived before, we can see that the intermodulation products depend on the input power, have a cubic dependence on the input power, right? And therefore, if we plot the input power in dBm and the output power in dBm, what we will find out, what we will find is something like this. We will find that the signals at omega 1 and omega 2 follow this dependence, which is the compression that we have seen in previous section, and the intermodulation product follow a line like this, right? These intermodulation products will also compress at some point, but the important thing is that here, this line, this asymptotic line, has a 3-to-1 slope due to this cubic dependence, whereas this line has a 1-to-1 slope, and therefore both lines will cross at some point, and this point where they cross is called the third order intercept, or the IP3. And accordingly, there are some defining terms that are used and that I will be using in following segments. We'll be using the input power as Pin. This is the input, the power of the desired signals. The IP3 referred to the input would be this. The IP3 referred to the output, it's this. This is the power of the desired signals at the output, and the IMD is the power of the intermodulation products at the output, right? The factor R is also plotted in this diagram, and one can see that the difference between this distance, this vertical distance, has to be R1/2, and that comes because if in this difference between the input power and the input IMP3, if it's projected through the third order line, will give us this distance. And if we project it to the 1-to-1 slope, it gives us this distance. So accordingly, this distance in here, this vertical distance, has to be 1/3 of the total distance between here and here. And therefore, in other words, this distance has to be 1/2 of this distance. So if we define this as R, which would be the intermodulation rejection, this distance in here has to be R1/2. So in this graph, I'm plotting all these defining parameters, and not shown in this figure is the small signal gain. The small signal gain in dBs would be the one required to go from the intermodulation, the IP3 referred to the input, to the IP3 referred to the output. This would be, the OIP3 would be equal to the IIP3 plus the gain in dB. And this concludes this section of the lecture.